Okay, so just to retrace and connect what we have been talking, we are talking the biomass feedstock, which is renewable feedstock, captured carbon biologically at one point of time. We want to keep in the system or sequester in the soil. Alright, so these are the feedstock we have been talking, and why we are talking about that? Because there is a societal need. Right? Fuel, food we need, energy we need, water we need. If I talk just one, let's say this one, microwave, is it contributing to fuel or not? Food, you go to high-end supermarkets, people take LG, okay, that is food, high-end food also. Microwave also is part of that. Omega-3 comes from that. There are many other compounds that can come from that. Energy, we have been talking, you can change into fuel. Water, clean water. Using tertiary water treatment or secondary water treatment. Same way, all of these are renewable, can contribute to that. The challenge I was talking yesterday. Now, look at 4 different transportation modes. Okay, what is important when we are transporting? The biomass feedstock is important. That's going to give you fuel or product. But it's not water free. Okay? Not as free. Some of the LG you see 15-20% inorganic material, even more than that we have seen there. That is not we want. When we transport, we are looking for organic material, how much we can transport. So if we have good one truck, we are transporting a lot of energy. And if you have some slabs or this kind of bulky material, you are not transporting a lot. So if you want to transport these things, because transportation is part, you cannot build one next to it. You have to bring things, right? So if you are transporting, what the option you have here? How to do that? Compact it, pelletize it, right? Then you can carry on. So that's one challenge. Moisture content I talked. Yesterday I focused a lot on oxygen. How oxygen plays a role in biomass. If you are looking for fuel or products, we don't want a lot of oxygen. The feedstock we are taking is full of oxygen. So the reactions when we design conversion, we focus on that. And that's a challenge. So one technology I was talking was sub and supercritical water or hydrothermal. We talked pyrolysis, gasification, maybe I'll come back again to those topics, but just want to continue the fix. So hydrothermal, what was hydrothermal anyone? Sub and supercritical water. Yeah. Use water for instead of methanol and ethanol or anything. It's like a green solid. Use water chemistry. Okay? That looks green, sustainable. What challenges and all? If you want to simplify, you are talking to someone who has no idea about hydrothermal and anything. Because as a student or a scholar, we talk to high school, middle school, farmers and everyone, and they need to understand your language, right? You cannot keep I publish this and this is the data and all. So if you want to simplify, you would say it's a pressure cooking. How you cook your food? So pressure cooking, water and cooking. This is a little more than that, but it's a way to simplify it. Okay, so if you don't close the lid, it's a steam. If you close the lid, it's mixed stage, water and steam. If you keep increasing higher, it will be more water, less steam. But if you cross 374 degrees Celsius, that's what you want to remember, roughly 24 megapascal, 25 megapascal pressure and 374 degrees Celsius, you get supercritical point. If you are working below 374, that is subcritical range. If you are working above, you are working in supercritical range. And both have applications. Lower temperature, you can make more liquid. If you are heating something at higher temperature, what you are expecting to make? More gases. So if you want to make syngas or hydrogen or even methane, you want to go beyond critical point. If you are looking for jar making or crude making, you want to keep indoors. So that's something. So this one I talked why water works, and not only biofuel. If you are doing any other chemistry and you are using some solvent, try water also. If you are using methanol, you can go to other side using water also as a baseline. So what water does, you put under temperature and pressure. Pressure is important here, and that's the cost, capital cost. Pressure cooker is costlier than open utensils, right? Because it's a thicker and heat and other things. And I'm talking much higher pressure than the pressure cooker. So it's a capital cost you have, but temperature you save, time you save, pressure cooking very quick. Alright? So time you save, temperature you save when you compare with pyrolysis and gasification. So you can do at a lower temperature, lower pressure, lower temperature and faster. Because when you heat water under water phase, density goes down. If density goes down, water, if you want to do two things in reaction, that's these two compounds, gas and this, and you want to react them together. How will you do that? This is solid, and you want to react them. How this you can do? Contact reaction, right? It's difficult. More surface reaction than all. Then you melt it, go to higher temperature, break it, then mix nicely, and then you can do that. So water, if you have, water can reach different pores. You can soak water and can reaction needs one good contact. If contact is better, then only reaction will be more efficient. Okay? Gases versus water. You have a porous material and you are pouring water, passing gas, which one will be more efficient? If you have porous material and you are passing gas, it will touch all the problems, right? Water may take some shortcuts and all those things, waiting many days. So water has some benefit because you have better contact, hydrolysis can go. Gas is low density, so it will go everywhere. But let's say if you have a mix of that, little lower density, not water, but little lower density, but not exactly gas. So you get in between of that works very well for the reactions. For mass transfer, heat transfer, it becomes a good medium. The dielectric constant, when we talk about the dielectric constant, solvent property, you can tell you. Higher the dielectric constant, more polar is the solvent. Lower dielectric constant, more non-polar. Why we worry about polar, non-polar? Because sometimes we react with oil, sometimes we react with methanol or more polar or water, right? So like dissolve like, and this is how water can be tuned. The only one solvent, but you raise temperature pressure or reduce temperature pressure, it will behave differently. So it has good solvent property. Viscosity also, its flow viscosity goes down. What gets better? Ionization constant. So you can see that they start here, and as you heat water, ionization gets better. Good for reactions. Okay? Then falls down, and this is log scale. Log scale. See, 1,000 times higher. Okay? In subcritical water range. When you go supercritical water range, become more free radical for gasification and also ionic constant is less, but more free radicalization. So this supports gasification process. So why I am bringing that? Because water is one of the most abundant solvent on the earth and has many good properties, and you can tune it the way you want. So it can support green chemistry no matter you work on biofuel or some other reactions. So coming to biofuel, how hydrothermal works. If you are working in lower range, 200, 180 in that range, it's like a more hot water, hot compressed water. You can extract from biomass. some compounds of interest from agriculture waste or energy, you can extract those. It's not very high temperature and resident time is less, so you can extract, and when you use water, you will be exposed to chemicals. You don't have to worry about the contamination, you can protect it. It's good for extraction. In bioethanol, we create the pre-treatment, so open up the pores and also pre-treatment of biomass you can do, that is used for bio. If you want to make biochar, in hydrothermal typically we call hydrochar, not biochar. If you do pyrolysis way, we call biochar. If you do hydrothermal way, we call it hydrochar, but it's a niche, some people still call biochar. Okay? So you can carbonize in subcritical water. So now you see HPC or hydrothermal carbonization, we are conducting 300, 250, 280 range. Pyrolysis, what temperature you do? 450, 400. So you save the temperature. Okay? If you are doing in water, what other benefit you get? What are the different products in pyrolysis? Gas, liquid and solid. Right? And gas you need to clean, but you cannot do it just like that. But there are many other things coming. When you are doing these things in water, do you have to clean gas? No, things are stuck in water already. So it's cleaner emission. But the water which you got, kind of many different compounds. So maybe wastewater treatment or nutrients recovery, or you can use for recycling and other things. So it has different chemistry. And if you want to make hydrogen or methane or not, go to a little higher temperature, 374, 380, 400, you can get it. So how we use this? So PC and Roshi. Critical temperature, critical pressure, critical density. 374, 22.1 megapascal and 0.375. That's where you are working. Advantages, now you can tell yourself. I don't have to repeat. No drying of biomass. Water will see all kinds of biomass. You don't have to depend on grass or wood or anything like that. Reduce mass transfer. That's what I was saying. Heat transfer, mass transfer, get better. We have better contact. And I showed you hydrochar, bio-oil, hydrogen. All three things by changing temperature, pressure, you can use for that. Challenges, it's not easy. You have to do batch process or high pressure required. So your capital investment is high. That's the challenge. And salt which was soluble at room temperature, it has started precipitating. So if you are doing some reaction and scaling is started happening because of salt, heat transfer gets poor and other things. But people are working on that, how to address this. Every process has challenges, and that's how we get research opportunity. Let's address that. Energy requirement, I said yesterday, if you have steam, it's 3 megajoule per kg, but if you are working in subcritical water, it's 1/3 because of you are not changing phase. Liquid remains liquid, so you don't have latent heat of vaporization. That's the energy goes when you evaporate water. You save that. So let's come back to this feedstock, which is carbon capture in form of microalgae. This is one of the lake in China. Okay? And there are many here also, and many US across the world. This happened why? Anyone? Why we see this kind of lakes covered with so much food? Because of excess amount of nutrients, eutrophication happens, and then you get. So it teaches you can grow so much of biomass rapidly if you have nutrients. Wastewater has nutrients. Can be used rapidly. Okay? So wastewater will pick up nutrients, grow healthy, clean water. Now this is biomass. If you are doing with clean water, then it has many high value compounds we can use for food and other things. This is from wastewater, so you might have some. So you don't want to propose for some high value food application or human application, but good for animal or other things. So it depends how you grow. Alright? Now this is treated as a biomass and convert, you address two things. Water treatment Putrefaction and biotic, multiple things you are doing. If you want to better culture, not like this, but you learn from there how it grows fast. Do some biology side and how we maintain so it has a better growth rate. Bring that knowledge in open pond or bioreactor. Now you have nutrient media, tune it, increase the productivity with light and nutrients management. You can do in photobioreactor. Now it's much more cleaner and controlled species. What you want to grow. Maybe it's still mixed culture, but not like wastewater. This has many different applications. Fuel, high-end products also can come from here. You can turn it into fuel, you can turn it into many attractive pigments, carotenoid, and many other things you can attract. And I was discussing water can be used for these things. So you don't have to go ethanol or hexane and then you contaminate and those things. Yesterday I was talking CO2 enhances power consumption. Okay, so CO2 enhances growth because Lg means carbon source. So you can place next to where carbon emission happening. CO2, smoke, flue gases and all. So you can do that. But second point I was saying, one time you are thinking place Lg next to plant, but it's not getting very simple because plant has different objective and maintaining a pond next to it becomes different. But does it matter where we throw it? It will capture CO2. Maybe you meted in Kishangarh and capturing here, it's same atmosphere. So you don't have to stay next to it. And direct air capture can work here. So we are solving the same problem in a different way. So once you cultivate, you can say that you can capture here. If you can place it here. If you cannot, place wherever it is, in the space and other things, knowledge base, because Lg cultivation and sugarcane cultivation or corn cultivation are different. Farmers knows how to cultivate corn. We don't have farmers who know how to cultivate Lg at such a large scale. You need a skilled workforce. So this is another part when you develop technology, you have to skill someone. Okay? So that's another part we should be looking. So this is agriculture, but it's different agriculture, aquaculture, close to aquaculture. So you take that Lg. This is pretty dilute, 1 gram, 2 gram per liter. The max in photobioreactor you go 3 gram per liter. Some of the labs have shown up to 4 or 5, but not more than that. That is nothing. It's basically water. Alright, 1 gram, 2 gram is very small. If you want to make anything out of it, you need more amount of it. So the way to do it, you concentrate, harvest and concentrate. And industry, when we talk about solid liquid slurry, typical thumb rule numbers are 10 to 20% slurry is the best for flowing, doing reactions. If you are much more than that, let's say you have 30-40% water, then it's basically solid dough. Very difficult to flow, reactions are not good. If you are too dilute, economics is not good, because you are running very small amount of water. If you are running around 10 to 20% slurry, that's the good amount to do that. So you have to think how to bring from here to here.
So how about hydrothermal? We use only 5%.
But
For hydrothermal liquefaction, suppose if I have microalgae and I don't want to harvest like solid, maybe I can concentrate that to 5%.
yeah, we have done that. And for population and combination of those things harvesting, you can go up to 10%, 15%. So it's a two-way step. Once you harvest, it will be lower and then you can further concentrate. But I have seen different species. Nanochlorosis, we have seen up to 8 or 10%, it grows 12%, then it becomes very thick. Then it becomes difficult. Some organisms and anastomos and all get gone up to 15%, you can grow.
We need to make it like how much H2O to this microalgae cells.
So when you are concentrating for conducting reaction down the line. per mole or pyrolysis or whatever. The economics, I am saying that economics work when you have more concentration. The other part of trade-off, if you have more concentration, it won't flow. So you will find a window.
Yes, for hydrothermal liquefaction, we generally use slurry. So that is what I am saying. That must be 8%, 10%, or we can go up to 4%.
So I'm coming. So if you can go even, this one also is ready for hydrothermal. You don't have to concentrate. But economics will not support. You will make all the products there, oil, everything. But with 4%, 2% is too less amount, the material which you are meat, what we say, it's very less. Okay? So dilute is not economical. Reactions are better in dilute, but economics does not work. Like fermentation. You want really 4% or more sugar in the broth, then you can distill and do that. Now you want to increase concentration to meet economics and do better. But how much can you increase? So if you go 15, 12 range, still you can mix where it can compete and do that. But if you want to increase, go to 30%, you are getting in different zones, paste. Then your mixing becomes tough, mass transfer, heat transfer, all those things. So what I will say that there is no single number, but think of flowable slurry. Concentrate here, still you can flow, and then put in a hydrophone reactor. That's the right concentration, I say. And that right concentration window is 10 to 20%. Like nanochlorosis, little less, anadosmos more, in that especially dependent, but that's the window you got. You can obviously work on 5%, but you won't make economic scale. But for research purpose, that's better. You are not worried how much you are producing. You want to get some simple analysis and understand chemistry. Okay? So I already talked how LG supports you. It can be very good food. That's what I was saying. The protein is high in demand. And if you look at the table of LG's basic and composition, you will see about 60% protein in some of the species. Some are 30, some are 40. So you can be a very good protein source. Supplement. Retinoid. These are dealt in gram and kg, don't need tons, alright? And they are there. You can extract nicely without decomposing them. There is opportunity. Cleaning water, it does, I thought. So wastewater treatment can be helpful. We have different wastewater, basically carbon, nitrogen, phosphorus, the source, nutrients. Now open, close, you can decide which way you want to go. You can do cultivation. Once you have the LG slurry, you can make all these products. Biofuel, animal feed, fertilizer. If it comes from green, then you can make protein for higher value application. Alright? Now, let's focus on here. Wastewater we use for LG cultivation. That means wastewater was source for nutrients, NPK, to capture energy, to clean water. Now you are taking LG and doing hydrothermal or pyrolysis and all that. You should keep an eye what we pick up nitrogen phosphorus where it is going. Otherwise, cleaning here, putting out something. Alright? That comes nutrient management in agriculture. Okay. want to be sustainable or nutrients also. If you get free from wastewater, it does not mean that we should exploit it down the line. So how we recover that nutrients back in wastewater and healthy values, and that's another nutrients management. So how you recover nutrients to grow back or supplement. Alright? Because nutrients A and B, even if you are making fuel out of it, nitrogen is not welcoming fuel. Phosphorus is not welcoming fuel. So better to design a process where you can recover it and put it back. So you can do biofuel, animal feed, biofertilizer from wastewater. If it is a clean water, fresh water, you can have instead of animal feed, you can have a high value of proteins. Considering harmful in the globe, how to deal with this? Think of a hydrothermal reactor which is mobile, truck loaded, on trolley. You bring it here, take this slurry, and do biofuel of that. You don't have to take it there. Yesterday I was talking that we published the IIT Institute of Petroleum, they got the LG2 jet fuel and then it was tested in plant. So it has been tested, you can make a drop-in fuel out of it, not blended, drop-in fuel, which is what this was blended, but you can make it. And there are a lot of materials you will see companies are making slippers, shoes and many other things, resins and other things. So it has a lot of other applications. If you have a healthy based biorefinery, think how many things you can make. And no one wants to make everything, right? You develop a business plan on something I need from this. And food additives, you can get it. Fatty acids of PUFA, you can get it. Proteins, you can get it. Fertilizer application can be there. I have seen projects where you cultivate in wastewater and that is just put in farm. Carbon and nutrients goes in the farm. It's biofertilizer. So it depends on what we are trying to do. Fuel definitely you can make it. Challenges I already talked yesterday. So see the species. Depending on the species, protein changes. So let's say we are looking at protein, then we will choose certain we are this one, synadosmos which has more protein. When we are cultivating synadosmos, we will tune the medium condition, light condition, here LG moves more towards protein than carbon. Okay, so we have the opportunity to do. But proteins means nitrogen. Right? Carbon, oxygen, nitrogen, nitrogen. There is no nitrogen in carbohydrates. Where does this nitrogen come from? It's your fertilizer, right? So more protein, more fertilizer you are putting. So how to take it, make it sustainable or recyclable? So whenever we are looking at LG based processes, we should be looking at how we are managing nitrogen plus other things. It's all atom economy. Carbon, nitrogen, nitrogen comes here. While have a bigger picture on jet fuel, you should not destroy nitrogen compound. Nitrogen is not there in jet fuel. So I not worry, drain it. That's another implication we are creating. Right? So we developed a process called flash hydrolysis, okay, in our lab. And this is, for last 14, 15 years we have been working in this process and it has shown some good potentials. So most of the talk I bring this also, that this is one potential process. So what we does, to take LG slurry, pass through a reactor, no chemicals. Okay? Think of a tubular reactor, can form this continuous flow reactor. Keep temperature 200 to 250 to evacuating, what you want to make, keep the temperature around that under pressure, subcritical water. And it easily fractionate. Okay? Proteins comes in this liquid phase. Most of the protein gets hydrolyzed in liquid phase. Most of the carotenoid and all will get mixed here. But if you are working on carotenoid, you need to choose the right temperature with you. But here the idea is to take all proteins here. So we get fractionated. The other fraction is solid. Solid, so if you are looking at biofuel, then liquids what you are looking for. And you don't want to disturb that, but that's our fuel material. When we do flash hydrolysis, all liquids stay here. You don't disturb it because temperature window is less. Fatty acids are still stable, so they stay here in solid. We started here which is protein plus everything. Now we came to after flash hydrolysis, we got this material which is still green, not carbonized, because we treat only 10 seconds. We have a continuous flow later for flash into it, just 10 seconds. So you get solids which is rich in lipids, all lipids are here, some carbs are there, very low amount of protein, and all protein is not here. Now this gives you lot of opportunity because this has nitrogen, phosphorus, all the minerals. You can think of what you want to do. You can recycle just to farm, it's a fertilizer. This is proteins, but not that deep chain protein, it's a smaller peptides. You can extract peptides, right? You are looking at some extractive carotenoid, you can see it's still there, you can extract that. And this one can go for fuel. And during doing everything, we are keeping an ion C and B atom balance. This is for us, it's a biomass, it's a carbon, nitrogen, phosphorus source. So how we are partitioning in different ways, they are in different compounds, but how we are balancing, that's what we are looking at. So most of the phosphorus are here, this is liquid fertilizer. It's not. So you can use as a liquid fertilizer. So these have many different applications. Yeah.
In case of industrial wastewater, you may have lot of pollutants, maybe some tricyclides, carcinogenic elements could be there.
Yeah.
So those may have some adverse impact on this hydrolysis or whatever the growth.
Yeah, so, yeah, I get it. So now what you are doing here is thermal process. 200 to 50 degrees Celsius just for 10 seconds. So microbial activities are gone at 200. Basically, that's right. Water is electrolyte basically. You won't see much growth. Alright? Maybe some phenolic compounds might be there.
Yeah, maybe very depends on source of.
But it depends what you want to do with this. If you want to recycle back to the pond and you see some still in battery, you can dilute it with more water. But this is a concentrated. This is a concentrated form. You can put some dilution. So it will have a less right?
The final product may have some this impurities.
No, so yeah, definitely. So definitely those final products, what we are looking for. See, it's a soup. Everything is there, right? Peptides and everything. Now it has to go to, if you are looking for high-end products, let's say you want peptides, then you have to go to chromatographic separation and then it will minimize contaminants there. Maybe you need a purification
So we
cycle.
have to add more steps so that we have to remove those pollutants.
Yeah.
Especially, but it may have a tedious process, right? Because there are variety of pollutants, so it depends on source of water.
Yeah.
So
Yeah, so that's what I'm saying. So you are right on the point. So if you are looking for, it depends on what you want to do.
okay.
So we are looking for a good high value compound. We are not looking at wastewater energy. Then you have a clean photobioreactor, and then you are looking at carotenoid using flash hydrolysis. If you are looking at wastewater, grown LG, then definitely you have a lot of pollutants, fluoride and many other things. Then when you do flash analysis, this is just nutrients you will treat like that. You got all nitrogen, phosphorus, fluoride, magnesium and all those things in liquid. So now it's good for medium. You can recycle back or you can use as liquid fertilizer. And if you see a lot of toxic there, you can dilute it. So
will it be possible in continuous?
this is continuous process, you cannot do in batch process.
Okay.
What I am talking is residence time is 10 seconds. If you keep it longer protein, what will happen to protein? If you heat half an hour protein, it will go back, right? Many compound will degrade. So this is why we call it flash hydrolysis. And can you do 10-second reaction in batch process? No, it has a heating time. You cannot do basically. So that's why we have a continuous process. Flash hydrolysis, subcritical water process. We have developed a trolley mounted.
Okay.
You can take next to the farm. And if you are doing photobioreactor and all, you can put it there for cleaner. And you see, we are not doing any chemicals.
So example already people are using there or still
So these are all part of LG research area. So you know how much commercialization
that's
happens.
true.
So we have brought to the pilot level, and this has been funded. This work has been funded a lot. 3-4 funding we got from National Science Foundation. They were interested in that. In fact, our initial publication, it was discussed in science paper also. Because in the beginning, everyone is thinking LG will take biodiesel or we'll do hydrothermal liquefaction and make crude.
Right.
We brought the idea that you are destroying protein in doing so. You are destroying fertilizers. Why don't you fractionate, which is anyway not welcome in crude? So take it out and then do whatever fuel or whatever. So this is a very good fractionation method. Good. We are showing from LG, but you can use for many other things. We tried for DDGS, distillate grain, which is high in protein, much cleaner source from ethanol plant. You can do flash hydrolysis, you can bring peptides out of it. One of the company was interested in food preservative, how to extract that. So the concept you can use for. So it's a concept we are applying here, but the concept is you have a multi-component system. Carb, proteins and all, how do you fractionate with minimum damage of each component? You will degrade it, but how you do minimum? People do ionic liquid, right?
Yeah.
In ionic liquid, it's a cleaner separation.
Yeah,
You can do that, you're not much mixing. But ionic liquid has its own challenges. You need a lot of liquid and how to recover and all. Here we are talking just water, little temperature, 200 to 50, 180, and then you can extract.
Does it need high the water quantity? Is it? Is it depends on the size of the reactor or?
No, it's a reactor size is very small because if you are talking continuous process, if your residence time is short, going reaction engineering, reactors are very small. If your residence time is 20 minutes, then the reactor becomes bigger because you need a tube where you can keep liquid for 20 minutes. Now you have to keep at 10 seconds, then you have to flush fast. So reactors are very compact. Okay, the only challenge is we are working on the high pressure system. So LG flows nicely. DDGS will not flow. Alright? It is a fibrous material, so it's difficult to make a nice blend. Those are the challenges. So it depends on which feedstock we are trying. And it's a fractionation method. So proteins are sensitive to temperature. So you want to work at temperature for minimum exposure time. So 5-10 seconds is still, but it's not fully degraded. So
Second, should be second.
seconds. So this process we have shown for 10 seconds, 12 seconds. So if you go more detailed, then there is a challenges.
Yeah, of course.
How you design a reactor where you have only 10 second class. So we have shown that you can design, we have shown on basis. So that's why we worked a lot in this and it got a lot of attention. In fact, after that, people have started, we'll see 10-15 years back, they started talking about fractionating LG. take proteins for something else. Otherwise, everything was crude or biological. Okay, so this gives a tool for fractionation, high value extraction. It got some application beyond the aging. So now water, we did in water phase. Okay, one of the challenges when you recycle water is to not have growth. That's gel and ammonia. So if you treat water at 200 degrees C, do you think any bacterial growth will be there? It's basically electrolytes, right? So if you can separate and put back water back in. So water is electrolyzed and can be recycled back. Once you extract the compound, water is still good to go back. You have a next to you is a wastewater treatment, you can give it to them. Once extracted, you can do that. Minimize degradation product, which we are talking, that is really dependent on contact time or residence time. If you are going 5 minutes, then protein and sensitive carotenoid and all they will degrade. But you are just like a microbe, not even microbe, just putting it and taking it out. Then it does not get enough time to degrade. Biofuels intermediate, we call it this compound because it has all lipids. So it's good for biofuels. So biofuel, this is high in carbon because it has more carbon percentage. And then it's good for the storage now. If you are looking for industry, you need inventory for a week or so to run an industry. You are not doing it every day and going through. This is good for inventory. This is a dry powder now, if you want, or slurry, which is sterilized now, so it's not going to biodegrade. You can store it. You can pelletize and transport it. So non-perishable solid is not going to biodegrade. So these things we have shown. So this is the setup I was talking. It started from here. 2 HPLC pump, high pressure pump, just to do that, furnace and see a reactor. This is the reactor, just water is tube, less than that. This is the pumping system we developed at lab scale. How to pass just within 10 seconds. We learned enough, then we went to this one, trolley mounted, and this was a student built. So we had a slurry pump which can pump slurry, and the reactor is only this much. And it gives gallon per hour, 3 gallons per hour you can run through it. Now you can take this to any LG from location. You can fractionate and solids you can store, liquid, some value need to be extracted, or put it back in farm or recycling tank, whatever you're working on. Wastewater you want to recycle, high value compounds, wastewater and you want to extract. So this is what we developed. And you see the coil, it's not a furnace.
I'm just curious to know that whether you make slurry or after harvesting biomass completely dry like scientific.
No, we never tried biomass.
Okay, so you directly go to
So in lab scale what we do, you can do many other ways. But at lab scale your focus is reactions and other things will not do. So harvest, you add coagulation, you can centrifuge and how much water to do. Right? You can do that. Place filter and you can squeeze it and get it. But people working in harvesting, they know how to concentrate, membrane.
I was just curious that if you are taking biomass, then you are making slurry after getting dry biomass or
No.
using dry?
If you dry and soak it back, change it. Right? LG is a biochemical compound, so things will change. So we are not drying at all. We are just removing water to the level where we want slurry. And we are not evaporating because again LG will
So
change.
you just take dense culture of microalgae
And you concentrate through centrifuge and
that is all weight biomass objects.
This is all wet biomass. And now here you see furnace and here you don't see furnace. Alright? This furnace I had to heat 600, 700 degrees Celsius to get 200 degrees Celsius inside the reactor. So this is passing so fast and you have to apply a lot of heat so that heat balance so you can have 800 degrees supply then liquid in 10 seconds will pick up. Then we came out that if can have induction heating. This is induction heating, like induction stove nowadays. It's very quickly. Yeah. Nowadays you can buy a stove with induction heating and you have a different utensils, but it heats very quickly. So even if you have batch process now, you can heat in 2 minutes. This one has capability of 200 degrees Celsius per minute. So within a minute you can rate, but now it's a continuous process. So just a start and this is maintains. You can pass within 10 seconds. And induction heating is electricity. Electricity to electricity is not thermal, so your efficiency is better. It's a high quality, right? And renewable energy, because you get electricity.
What is the injection volume of this slurry, for example?
So this one, this pump is, it's a throughput, so 2.5 to 3 gallon per hour, depending on what concentration of slurry you got.
Yes, and that you convert that with this.
So you have a tank, which is not steam here. So tank pumps, disposes, passes through reactor, you collect here and you can fix it. That's all simple system. Now when we tank less 8 to 10% slurry. We have done with 2% also, but we won't get much LG out.
Then you do hydrothermal liquefaction or flash?
Now it depends. I'll go back.
Flash
Now.
hydrolysis.
I'll go back now. That will be here. So now we did this. Alright? Got liquid and solid phase. This is we call good for biofuels. We named it biofuel intermediate. From here, we want to decide we want to make jet fuel. Okay? We can go hydrothermal again and crude. You can go even pyrolysis because it can be dry. You leave this at 200 and do some engineering, cooling, heat recovery, you can dry this. You don't have an extra heat to supply. You supply one, then you can integrate it. Alright? So you can go pyrolysis. So what suits, but we have seen that, I will show you other paper, where we do another hydrothermal. Now this crude, or if you do hydrothermal here, this is much better crude. No nitrogen, very low amount of nitrogen, no phosphorus, everything on here. Now you can make jet fuel out of it. Good quality. We publish it, we did with Enwell.
Yes, even during the culture time, when we will be actually growing the culture, at that time also we can have in the stationary phase, we can maintain high CN ratio in the beginning, and that will actually promote microalgae to accumulate more liquids.
Yeah.
So in that way we will have more liquids, and at that time we can harvest, so we will not need to change again.
Yeah, so this video, this is a process. This one we have control what we want to grow. This water, high liquid, like manipulating the fermentation. So this is your feed of what you want. More protein, more liquids. I'm industry, I'm worried about proteins or carotenoid, then our LG will be tuned to growth accordingly. If you are worried about liquids and fuel, then we will tune the growth condition, nitrogen requisition, and also have more liquid accumulation. So that's cultivation results. Once you did that, the challenge is how to separate. If you don't separate and do this in hydrothermal, basically it's cooking soup. You don't know how many things are there, how to use it. What we are doing, you can fractionate and then you start.
Yes. So we did some work on this. We actually extracted PUFA first. So all those valuable compounds have been removed, and later on only saturated fatty acid were inside, and then we went for the
Yeah. So I will tell you the niche area, why we named it and it got attention and all. It's very difficult to design continuous process setup with 10 second, 12 second response time. That's the niche point we developed. There are many other groups in hydrothermal. They started working and they developed 2-stage hydrothermal. Reliance here, we got with them. They had 2-stage hydrothermal. First stage, you do this, remove this. second estate you do another estate. But their residence time 1 minute, 2 minutes, you cannot be done. So when you do 1 or 2 minutes, you don't have those Kufa and all, they are all gone.
Yeah.
So they are only nutrient source now.
Yes. And secondly, if you want to lower down the cost of the biodiesel,
Yeah.
then we should go for valuable compound first.
Yeah, valuable compound first. So if you are doing valuable compounds and 1 minute, 2 minutes, they are not valuable compounds with temperature and all.
Yes.
So that's the niche area we developed, and that's why we got attention and a lot of application came from our this. And now what I'm saying, this concept can be used for any other fractionation. It's not just designed just for it. It's a concept. So this is the reactor. You don't see furnace because we have induction heating here. We collect samples here and we just leave it for some time. We have to fetch solid and liquid. So it's simple filtration we separate. Okay. Now this is the liquid collected. Solid once you separate, we took some sample of that mixture. The solid will sit at the bottom and this will separate nicely. The liquid looks like this. Okay. If you freeze dry, looks like this. We were thinking about proteins, so the high protein. So protein will break down, hydrolyze, right, at temperature. Protein molecular weight more, then it becomes peptides, then it becomes amino acids. That's how it is like glucose. So these are peptides, not that big molecules, peptides, intermediate, which are water soluble. We just freeze dried for analysis purpose and understanding purpose only.
Characterization.
Yeah, characterization and all. And we looked at that. Nitrogen content in this liquid or freeze dried is 11%. You don't see 11% nitrogen in normal feedstock, which is not reaching protein. In general, protein calculation 6.25 times nitrogen, we say estimation is this. But it varies what biomass you have. If you multiply 11 into 6 point something, 70% protein, so you can say this is 70%. There are other compounds. Carbon is still in the range, it's not 60 or something, which is carbonized. So now we took this material and we showed that what different things you can do. Again, it's a refinery concept, someone will want this one or this one, and all are published, you can tell it. So take that and nutrient recycling. What we did? A lot of nitrogen and phosphorus in this. You saw the protein is nitrogen here. Nitrogen, alright? It's a good medium for growing something. We recycle this liquid back to grow LG and recycle it for fine. You don't have to supply extra nutrients. In the second one, we did that. You can precipitate nitrogen and phosphorus in this in form of H2 H2 is called MAP, magnesium ammonium phosphate. Okay? You can precipitate almost around room temperature, and that's another fertilizer. Magnesium ammonium phosphate, magnesium in nutrient, ammonium in nutrient phosphate. And then we took that. This one we use for cultivation of LG, but this is a fertilizer to cultivate other things also. This concept is you have to recycle everything. Here you can precipitate and just recycle water, keep this as a fertilizer or you can transport wherever you want. This one you cannot transport so much. Here we did amino acid source. So we saw that amino acid was high in this. This was Senadosmas. So this is supplement, food supplement or something, arginine and all. So we saw that can be done. Another application, we did amino acids are used in carbonation and foam production. We take some samples, collaborated with Michigan State, and we showed that foam quality is still healthy. We blended only 10%, but it's a good replacement. And foam industry, you see how big it is. So another application we showed that artificial teeth So you add little bit calcium here, phosphorus is already here, and in hydrothermal condition you get precipitate hydroxyapatite methyl iodide. So see, if you are coming from wastewater, you will not go this side. But if you are doing fresh water, there is able to go. So we showed that you can fractionate and you can have, there are more applications like omega-3 and other things. You can do that.
What would be the byproduct outcome? I'm just curious about in the case of polyol and hydroxy.
So this is a blending material in foam making. So you need amino acid compounds in foam making if you go in that. That protein comes from soy protein. Now we have showed that instead of soy, which is food item, can replace with some of the soy. Okay, so this is foam industry, whatever byproduct from foam industry, we replace part of soy protein with them. So these are the applications for glass hydrolysis. Now look at the solids, what we did with the solids. The solids are, you need at different temperature for glass hydrolysis and you see it still looks green. If you put solids at a high temperature, it will turn carbonized, right? Dark. But we are subjecting only 10 seconds, 12 seconds. So it's not degraded. Maybe very partially, but not. Then we cool that and look at lipids. So if you have not done flash hydrolysis, it's a raw LG. Liquid content of synonymous phosphorus 15%. But now we did flash hydrolysis with temperature. It's simple math because if you move something, the percentage gone up, and now this is 67%, 70%. So if you are giving a feedstock which has 70% feedstock protein and lipids, it's good for fuel. If you do hydrothermal in this, you get cleaner oil, much more oil. We took bio fuel intermediate and solid, and we did sustainable aviation fuel for that, right? And we got good quality kerosene range, not much contamination. If you do directly, you will have protein, nitrogen contamination, phosphorus contamination. So, well, it's much more detailed. I'm just simplifying here. How you do that? This is 60-70% oil. You can extract, and you can do differently, or you can go totally hydrothermal. So it is both ways. This one was we added propane directly as a hydrogen source, and extraction in situ extraction. And it gave one of my students did that, and we got good quality. So there was no hydrogen supply for this. You could do in situ hydrogenation. Remember, biofuel, biomass with the stock is hydrogen deficient. So we have to supply hydrogen at certain states. So this is where you want to supply hydrogen. So you have the option to have hydrogen gas or propane or something else, propanol or higher hydrogen content amount, which breaks down the supply in situ. If you extract oil, then still you come out with the residue, am I right? You made biofuel, you do hydrothermal, still you will have some solid there. That's residue. So the residue we used and potassium carbonate we try to impregnate, and we get biocarbons sheet like this. It's nice uniform sheet. Okay? So we call it biocarbon. It can have many different materials applications. So remember, we started with LG and atom economy. If we talk carbon, nitrogen, how you handle, we handle in such a way that all things are mixed here. Within the soil. If you do direct hydrothermal, you are creating waste of some material. Here we almost, it's not 100%, but almost close to refined concept.
Is it out of
Residue material after that.
I mean, temperature or what specific reaction you need it for?
This one is kind of You have the alkali fluid and application process, thermal application process on that is done at 700, 600. This was I believe 600. Because you get carbon, then you have to impregnate and activate it to a high surface area. So we use PVA just machine, carbon application, very small amount. But we are getting good quality material here which can have any different applications. It's a nano sheet.
So you, excuse me sir, in case of this carbon nanosheets, you have measured surface area.
Yeah, we have done surface area. So I can share the publication on this one.
Okay,
Yeah,
so approximate size of this sheet is approximate size.
It's
This
a
sheet,
nano.
sheet.
No, you have to look at the TM microscope.
That
Then you will
is
see that
maybe-
it's a powder. It's a powder which is very porous powder. You have to do EM or SEM to look at the surface. It looks porous.
This is porous carbon.
Yeah. We didn't make any sheet of it. Just a powder and we looked at how this powder
Like biothermal.
biocarbon. This is biocarbon. We had a collaborator came from Mexico and she was interested in beta carotene. So we had a chlorella we tested and we did some study, but flash hydrolysis condition was milder in this case. 180, 150 that range. So we could see that we can protect beta carotene extract in water. Now you have to concentrate and separate as different, but we did that. So that was work with LG, and the concept is biorefinery and mostly use of water, water temperature. When if you do hydrothermal of intermediate, that's water. So there are many other processes you can do, but LG is a biocapture, biological capture, and utilization in different products. It is CCUS. You just say CCUS, you look very complex, but it is something which you can relate every day. I'll tell you some work on biomass unit, that was LG. And we tried to use water only for biomass.